Look up on a clear night, away from the glow of cities, and you will see something every human who has ever lived has seen. Stars. Thousands of them scattered across the darkness like distant campfires. For most of human history, this sight inspired wonder. It made us feel small, but it also made us feel centered. The stars were there. We were here. The universe seemed ordered, structured, almost understandable. It felt like there was a place for everything. That sense of order did not survive the 20th century. About 100 years ago, we discovered something that quietly dismantled our intuition about the universe. The cosmos is not static. It is not frozen in place. It is expanding. Every galaxy beyond our own is moving away from every other galaxy. And the farther away it is, the faster it recedes. This is not theory. It is not speculation. We can measure it directly in the light itself, stretched and reddened as space grows between distant galaxies. At first, this discovery seemed simple enough. The universe is getting bigger, but almost immediately it raised a question that refused to go away. If the universe is expanding, what is it expanding into? The question feels obvious, natural, almost unavoidable. When a balloon inflates, it expands into the air around it. When a city grows, it spreads into the countryside beyond its borders. When anything we know expands, it moves into something that was already there. So, surely the universe must be doing the same. Surely there must be something beyond it. But the universe is not a balloon. It is not a city. And the intuition behind the question may be wrong. This problem has haunted physicists and philosophers alike, not because it is complicated, but because it forces us to confront the limits of how our minds work. We evolved to think in terms of surfaces and edges, containers and boundaries. Inside and outside are among the most basic concepts we have. We understand what it means for something to be surrounded, but the universe does not care what our minds evolve to understand. Throughout history, we have repeatedly assumed that existence has edges. We believed the Earth was flat, with a boundary you could fall off if you traveled too far. When we learned the Earth was round, we imagined the solar system as a kind of cosmic island, with an edge where the sun's influence ended. Then we discovered the galaxy, vast and spinning, and we assumed that must be the boundary. Surely beyond our galaxy lay the final emptiness. Each time, we were wrong. The Earth has no edge because it curves back on itself. The solar system fades gradually into interstellar space, with no sharp boundary. The galaxy is just one of hundreds of billions, scattered through a cosmos so large that language itself begins to strain. Every time we thought we had reached the edge disappeared. But this question feels different. Asking what lies beyond the universe is not like asking what lies beyond a continent or a star system. It is not about discovering a larger container. It is about asking whether the idea of a container applies at all. The expansion of the universe is real. We have measured it with extraordinary precision. We have traced it backward through time. We can reconstruct how galaxies move, how light stretches, how space itself grows. But understanding expansion is not the same as understanding what it means for space to grow. When astronomers say the universe is expanding, they do not mean that galaxies are flying outward into pre-existing emptiness. They mean that the distances between unbound objects are increasing because space itself is stretching. A familiar analogy is a balloon with dots drawn on its surface. As the balloon inflates, the dots move farther apart, but the dots are not moving across the surface. The surface itself is changing. In our universe, galaxies are like those dots. Space is the surface. And here is where intuition breaks. The balloon analogy works only if you imagine the surface, not the air around it. The air is not part of the analogy. There is no higher dimensional room the universe is expanding into. There is no external space waiting beyond the edge. As far as physics can tell, space is all there is. This expansion happens everywhere, all at once. There is no center, no edge, no special location. Every observer sees the same pattern. Distant galaxies moving away, with speed increasing with distance. And then, in the late 20th century, the story became stranger. Astronomers studying distant supernovae expected to find that the expansion was slowing down. Gravity pulls matter together. Over time, it should gradually decelerate the outward motion that began with the Big Bang. Instead, they found the opposite. The expansion was accelerating. Something was pushing against gravity. Something was driving space itself to stretch faster and faster. We named this influence dark energy, not because it is understood, but because it is not. Dark energy appears to make up nearly 70% of everything in the universe. It does not thin out as space expands. As space grows, more dark energy comes into existence, filling the new space and pushing even harder against gravity. The universe is not just expanding, it is being pulled apart. This acceleration means the question is no longer academic. It is no longer just philosophical curiosity. It shapes the ultimate fate of everything that exists. Galaxies not bound together will drift beyond reach. Light emitted today will never arrive. Regions of the universe will disappear not because they are destroyed, but because space grows too fast between us and them. And still, the question remains. If space itself is expanding, if there is no outside, no container, no edge, then what does into even mean? To answer that, we must first let go of the idea that the universe behaves like anything we know. And in doing so, we begin to glimpse just how strange reality truly is. When we say the universe is expanding, we do not mean what you might think we mean. This is the first place where intuition betrays us, where the words we use carry the wrong implications, where our everyday experience becomes a poor guide to cosmic reality. Imagine a flock of birds scattering across the sky. They fly apart from one another, moving through the air, wings beating, each one traveling through space that was already there. Or picture a crowd dispersing after a concert, people walking in different directions through streets that existed before they arrived. This is how we naturally think of things moving apart. Objects traveling through a fixed, unchanging background. Space as a stage and motion as the actors moving across it. But the expansion of the universe is not like this at all. Galaxies are not flying through space. They are not traveling in the way a bird flies or a person walks. Space itself, the fabric of reality that contains everything, is stretching, growing, gaining distance between every point and every other point. The galaxies are not moving through space. They are being carried by space like raisins in a rising loaf of bread, embedded in a medium that is itself expanding. This is what we mean by the metric expansion of space. The distances between things increase not because the things are moving, but because the measuring stick itself is growing longer. You have probably heard the analogy of dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart from one another, but no dot is moving across the rubber surface. The surface itself is stretching, and the dots, stuck to that surface, are carried along with it. Every dot sees every other dot moving away. None of them is at the center. The expansion is the same everywhere, seen from every point. It is a useful analogy, but like all analogies, it is imperfect. The balloon expands into the air around it. The balloon has an outside. And this brings us right back to our original question. the one we are trying so carefully to approach. The universe, as far as we can tell, does not have an outside in the same way. But we will get there. For now, let us stay with what we know. This expansion was first observed by Edwin Hubble in the early 20th century, though the theoretical groundwork had been laid by others before him. Hubble measured the light from distant galaxies and found something remarkable. The light was shifted toward the red end of the spectrum, not because the galaxies were glowing red, but because the space between us and them had stretched while the light was traveling. Stretched space means stretched light, longer wavelengths, a shift toward red. And the farther away a galaxy was, the more its light was shifted. The more space the light had to travel through, the more stretching had occurred. This led to a startling conclusion. The universe is expanding, and it has been expanding for a very long time. Distant galaxies are receding from us, and the most distant ones are receding faster than anything we can easily comprehend. In fact, galaxies sufficiently far away are receding faster than the speed of light. This sounds impossible. We are taught that nothing can travel faster than light, that the speed of light is the universe's ultimate speed limit. And this is true in a sense. Nothing can move through space faster than light. But space itself is not bound by this rule. Space can stretch at any rate. A galaxy billions of light years away is not moving through space faster than light. But the space between us and that galaxy is growing so quickly that the distance increases faster than light could ever cross it. This is why there are galaxies we will never see, no matter how long we wait. Their light is traveling toward us, yes, but the space between us is growing faster than the light can cross it. The light makes progress, but the finish line keeps moving away, always just out of reach. These galaxies lie beyond what we call the cosmic horizon, the boundary of the observable universe, though they are still part of the universe itself. Now, you might wonder why we do not see this expansion in our everyday lives. Why does the space between you and the wall not stretch? Why does the solar system not grow larger? Why do galaxies themselves not tear apart? The answer is gravity and the forces that bind matter together. Expansion only dominates at the largest scales, where the distances are so vast that gravity's pull becomes weak and diffuse. Here on Earth, gravity holds you to the ground. It holds the atmosphere in place. It keeps the planet intact. The electromagnetic forces between atoms keep your body from flying apart. The gravitational dance between Earth and the Sun keeps our orbit stable. Even entire galaxies are bound tightly enough by their own gravity that expansion has no effect. Our Milky Way and the Andromeda Galaxy are actually moving toward each other, pulled together by mutual gravitational attraction, completely overwhelming any expansion of space between them. Expansion wins only in the vast spaces between galaxy clusters, where gravity's grip is weak and the stretching of space can proceed unimpeded. It is there, in those immense voids, that the universe grows. And here is the strange beauty of it. There is no center to this expansion, no single point from which everything is moving away. Every observer in every galaxy sees the same thing: all distant galaxies receding, all space stretching equally in every direction. You could travel to the most distant galaxy we can observe, and from there, you would see the same pattern. Everything moving away, expansion in all directions, no center, no edge. This tells us something profound. The expansion is not happening at some particular location. It is not spreading out from a point. It is a property of space itself, happening everywhere, all at once. But if space itself is expanding, this raises an even stranger question. Expanding into what? To approach this, we need to consider whether the universe is finite or infinite. The question of whether the universe is finite or infinite is one of the oldest in cosmology, and it turns out to be central to understanding what expansion might mean. Because if the universe is infinite, it has always been infinite, even when it was denser and hotter. And if it is finite, it might still have no edge, no boundary, no place where space simply stops. This requires us to think carefully about shape. Not the shape of objects in space, but the shape of space itself. Imagine you are a two-dimensional creature living on a surface. You cannot perceive up or down, only forward and backward, left and right. Now, there are different kinds of surfaces you might inhabit, and each would feel different if you explored them. You might live on an infinite flat plane, stretching forever in all directions. Walk in any direction for any distance, and you would never come to an edge, never return to where you started, never find any boundary at all. This surface is infinite. It has no edge, and its geometry is what mathematicians call flat or Euclidean. Parallel lines stay parallel. Triangles have angles that add up to 180 degrees. Everything behaves the way we learned in school. Or you might live on the surface of a sphere. Walk in any direction long enough, and eventually you would return to your starting point. The surface is finite. It has a definite area. But there is no edge, no boundary, no place where the surface ends. You could travel forever without ever finding a wall or a cliff, or a place where space simply stops existing. The geometry here is different. It is curved, positively curved. Parallel lines eventually converge. Triangles have angles that add up to more than 180 degrees. The rules are subtly different. There is a third possibility. You might live on a saddle-shaped surface, curving in opposite directions. This surface has negative curvature. Parallel lines diverge. Triangles have angles that add up to less than 180 degrees. And this surface, like the flat plane, could extend infinitely. Now, return to 3 dimensions. Our universe could have any of these geometries just extended into one more dimension. It could be flat and infinite. It could be positively curved, finite but unbounded, wrapping back on itself like the surface of a sphere. Or it could be negatively curved, infinite and saddle-like in its geometry. For decades, cosmologists have tried to measure which of these describes our universe. They have looked at the cosmic microwave background, the faint afterglow of the early universe, searching for patterns in the temperature fluctuations. They have measured the angles of triangles formed by distant objects. They have tested the geometry of space with exquisite precision. And the answer, as far as we can tell, is that the universe is flat. Or at least, it is extraordinarily close to flat, so close that any curvature is too small to detect with our current instruments. If the universe is curved, the radius of that curvature must be vastly larger than the observable universe itself. This suggests, though it does not prove, that the universe is infinite. A perfectly flat universe would extend forever in all directions. No edge, no boundary, no center. Just space going on and on, filled with galaxies and clusters and voids, all the way to infinity. But here we must be careful. There is a difference between the universe and the observable universe. The observable universe is the region of space from which light has had time to reach us since the beginning. It is a sphere centered on us, with a radius of about 46 billion light-years. Not 13.8 billion, which is the age of the universe, because space has been expanding while light traveled, stretching the distances. This observable universe has a boundary of sorts, not a physical boundary, not an edge in space, but a horizon. Beyond this horizon lie galaxies whose light has not yet reached us, and in many cases, never will. But those galaxies are still part of the universe. The universe itself extends beyond what we can observe, perhaps infinitely. If the universe is infinite, then it has always been infinite, even at the moment of the Big Bang. It was infinitely large then, just infinitely dense. Every point in space was pressed up against every other point, but there were still infinitely many points. Expansion did not make the universe larger in the sense of going from finite to infinite. It made the distances between things larger. It made the density lower. But infinity remained infinity. If the universe is finite, then the situation is different, but equally strange. A finite universe could still have no edge. It could curve back on itself, like the surface of a sphere, but in 3 dimensions. Travel far enough in one direction, and you might eventually return to where you started, having circumnavigated the entire cosmos. But there would still be no boundary, no wall at the edge of space, no place where you could reach out and touch nothingness. Either way, whether the universe is finite or infinite, the concept of an edge, a place where space ends and something else begins, does not seem to apply. If the universe is infinite, there is no edge because there is always more space. If the universe is finite but curved, there is no edge because space wraps around on itself. This is deeply unsettling to our intuition. We want there to be an edge. We want to be able to ask what is beyond that edge. But the universe does not offer us this satisfaction. And yet, the observable universe does have a kind of boundary. The cosmic horizon is real. It is the limit of what we can ever see, ever know, ever interact with. Light from beyond this horizon will never reach us. The expansion of space ensures that. In a sense, this horizon is our edge, even if it is not an edge of the universe itself. We are trapped, in a way, inside a sphere of visibility, surrounded by an infinite or finite cosmos that we can never fully explore, never fully map, never fully comprehend. Whether finite or infinite, the universe's expansion suggests it had a beginning, and understanding that beginning transforms our question entirely. If the universe is expanding, then it was smaller in the past. This is not speculation. It is simple logic running the clock backward. If galaxies are moving apart today, they were closer together yesterday, closer still a year ago, even closer 1,000,000 years ago. Keep going back, and eventually, everything in the universe was pressed together into a volume almost unimaginably small and dense. This is where the expansion leads us when we trace it to its origin, not to a point in space, but to a point in time, a beginning. Roughly 13.8 billion years ago, the universe as we know it emerged from a state of incredible density and temperature. We call this moment the Big Bang, though the name is misleading in almost every way. The Big Bang was not an explosion. Explosions happen in space, throwing matter outward from a central point into the emptiness around them. The Big Bang was not like that at all. There was no center. There was no surrounding emptiness. There was no where for it to happen, because space itself did not exist before this moment. Or rather, space and time came into being together, and asking what happened before the Big Bang is like asking what lies north of the North Pole. The question contains an assumption that does not apply. Time itself began with the Big Bang. Not time as we measure it with clocks, but time as a dimension, a direction in which cause can precede effect, a framework in which change can occur. Before the Big Bang, there was no before, no earlier moment, no prior state from which the universe emerged. The Big Bang marks the boundary of time, the edge not of space, but of history itself. This is extraordinarily difficult to grasp. Our minds are built to understand sequences. First this happened, then that happened. Every event has a cause, and every cause is itself an event that came before. But the Big Bang breaks this chain. It is the first event with no prior event to cause it. Or perhaps it is not an event at all, but the beginning of events, the point at which the possibility of events came into existence. When we say the universe was hot and dense in its earliest moments, we mean something almost beyond description. The temperature was so high that matter as we know it could not exist. Atoms could not form. Even protons and neutrons could not hold together. The universe was a seething soup of fundamental particles and radiation, all of space filled with energy at densities our laboratories cannot begin to reproduce. And this state existed everywhere, not at a single point, but at every point. The Big Bang did not happen somewhere, it happened everywhere, all at once. Every location in space, every galaxy we see today, every atom in your body was present in that hot, dense state. Not as separate things, but compressed together, occupying a volume far smaller than they do now. If the universe is infinite now, it was infinite then. Infinitely large, infinitely hot, infinitely dense. If the universe is finite, then it was still everything that exists, just squeezed into a much smaller volume, every point touching every other point. Either way, there was no outside, no surrounding void into which the universe was born. The Big Bang was not an explosion of matter into empty space. It was the emergence of space itself, along with everything in it. We have evidence for this beginning. The cosmic microwave background radiation fills the entire sky, a faint glow left over from when the universe was only a few 100,000 years old. At that time, the universe had cooled enough for atoms to form, and light could finally travel freely through space without being scattered by free electrons. That light has been traveling ever since, stretched by the expansion of space into the microwave range, a whisper of the universe's infancy still echoing through the cosmos. The abundance of light elements, hydrogen and helium and traces of lithium, matches the predictions of Big Bang nucleosynthesis, the process by which these elements formed in the first few minutes. The distribution of galaxies, the large-scale structure of the cosmos, all of it points back to this beginning, this moment when everything emerged from an almost incomprehensibly dense state. But what about the singularity? The idea that if we run the clock all the way back, the universe shrinks to a point of infinite density, infinite temperature, zero volume? This is where our physics breaks down. General relativity, the theory that describes gravity and the curvature of space-time, predicts a singularity at the very beginning. But we know this prediction cannot be entirely correct, because general relativity does not account for quantum mechanics, the physics of the very small. At the scales we are talking about, quantum effects should dominate. We need a theory of quantum gravity to understand what really happened at the earliest moments, and we do not have such a theory yet. The singularity is a signpost indicating the limits of our current understanding, not necessarily a description of physical reality. What we can say is that space and time began together, that the universe has been expanding ever since, that everything we see, everything we know, everything that exists emerged from this beginning. Not from a point in space, but from a point in time, or perhaps more accurately, from the boundary of time itself. This changes the question we started with. If space itself emerged with the Big Bang, if there was no space before that moment, then asking what the universe is expanding into becomes even stranger. Expansion does not mean spreading into pre-existing emptiness. It means the creation of new distance, new space, as time moves forward. The universe is not expanding into something, it is expanding, period. Space is growing and there is nothing outside of it for it to grow into, because outside is not a place. It is not even a concept that applies. Yet even with this understanding, our intuition rebels. If the universe is everything and it is expanding, there must be something beyond. Unless we have been asking the wrong question. Perhaps the problem is not with the answer, but with the question itself. Perhaps we have been asking something that does not quite make sense, using words that carry implications they should not carry, assuming a framework that does not apply to the universe as a whole. When we ask what the universe is expanding into, we are implicitly assuming that the universe is an object embedded in something larger, a thing inside a container, a balloon inflating into a room, a city spreading into the countryside. Every expansion we have ever witnessed in our daily lives involves something growing within a pre-existing space, a background that was there before and remains there after. But the universe is not an object in this sense. It is not embedded in anything. There is no background, no container, no larger space that holds it. The universe is space. All of it. Every direction, every distance, every location. And when space expands, it is not pushing into something else. It is simply becoming larger, adding distance between points, stretching the fabric of reality itself. This is where language begins to fail us. The word into implies an exterior, a beyond, a destination. But there is no exterior to the universe. There is no beyond in the spatial sense. The universe is complete in itself, a self-contained whole, not a subset of something larger. In mathematics, this is described using the concept of a manifold. A manifold is a space that is complete unto itself, requiring no external embedding to exist. The surface of a sphere is a two-dimensional manifold. It curves through three-dimensional space in our imagination, but mathematically, it does not need that three-dimensional space to exist. The surface itself, with its own intrinsic geometry, is complete. You can do geometry on the surface without ever referencing anything outside it. Our universe is a four-dimensional manifold, 3 dimensions of space and 1 of time, woven together into what we call space-time. This manifold has its own geometry, its own curvature, its own structure, and it does not need to be embedded in anything larger to exist. It simply is. When the universe expands, the distances within this manifold increase. The metric, the mathematical description of how to measure distances, changes over time. But the manifold itself is not pushing into some higher dimensional space. It is not occupying more room in a container. The very idea of outside the universe may be meaningless, a linguistic artifact with no corresponding reality. This is deeply unsatisfying. We want there to be something beyond. We want the universe to have an exterior even if we cannot reach it, even if we cannot see it. Our minds crave boundaries and containers. We understand nested structures, rooms inside buildings, inside cities, inside countries, inside the world, each level contained by the next. Surely the universe must be contained by something too. But there is no requirement that reality conforms to our preferences. No law of nature that says the universe must make intuitive sense to creatures who evolve to hunt and gather on an African savanna. The universe is under no obligation to be comprehensible in the way we want it to be. Now you might ask about higher dimensions. If our universe is a 3-dimensional space embedded in a 4-dimensional, or 5-dimensional, or 10-dimensional space, then perhaps it could expand into those extra dimensions. Perhaps there is a hyperspace that contains our universe, the way 3-dimensional space contains a 2-dimensional surface. This is a possibility that some theories explore. String theory, for instance, suggests that our universe might have additional spatial dimensions beyond the three we experience, tiny and curled up, so small that we cannot perceive them. In some formulations, our universe could be a three-dimensional membrane, a brain, floating in a higher dimensional space called the bulk. But even if this is true, it does not answer the question in the way we might hope. Those extra dimensions, if they exist, are still part of the universe in the broader sense. They are still part of the total reality, the complete structure of existence. And if we ask what that total reality is expanding into, we are back where we started. The question just moves up a level. It does not go away. Moreover, those higher dimensions, if they exist, are not necessarily places you could go. They are mathematical dimensions, directions, orthogonal to the ones we know. You cannot point toward a higher dimension. You cannot travel into it by moving in any direction you can perceive. It is not out there in any sense that maps onto our experience. So we return to the central realization. The universe does not expand into anything. Expansion is not motion through space. It is the growth of space itself. And space, being all there is, has no exterior. This might seem like a cheat, a way of avoiding the question rather than answering it. But it is not evasion. It is precision. It is the recognition that our question was built on a faulty assumption. The assumption that expansion requires an exterior. Physics describes the universe as a complete, self-contained entity. The equations do not require an outside. They do not reference any external space or higher dimension or containing structure. The universe is simply the totality of space-time, and its expansion is an internal property, a change in the metric that describes distances within it. If this feels unsatisfying, if it leaves you wanting more, you are not alone. Every physicist and cosmologist who has grappled with this question has felt the same unease. But sometimes the universe does not provide the answers we want. Sometimes it asks us to let go of concepts we thought were fundamental. Sometimes it asks us to accept that not every question has an answer that satisfies our intuition. Still, theoretical physics offers speculative frameworks, not answers, but possibilities that stretch even this understanding. While our best understanding suggests the universe needs no exterior, theoretical physics has explored possibilities that stretch this conclusion in unexpected directions. These are not established facts. They are speculative frameworks, mathematical explorations of what might be, built on principles that extend beyond what we can currently observe. But they offer glimpses of how beyond might have meaning after all, though not in the way we originally imagined. One of these frameworks is eternal inflation. The theory of inflation proposes that the very early universe, in the first fraction of a second after the Big Bang, underwent a period of exponentially rapid expansion. This expansion smoothed out irregularities and set the initial conditions for the universe we see today. But in some versions of this theory, inflation never completely stops. It continues in some regions of space, even as it ends in others. In this picture, our observable universe is a bubble where inflation ended, allowing matter and energy to settle into the galaxies and stars we see. But beyond the boundaries of our bubble, inflation continues. And in that eternally inflating space, other bubbles form, other regions where inflation ends, and new universes begin. Each bubble is effectively its own universe, with its own laws, its own constants, its own history. These bubble universes would be separated from one another by regions of inflating space. The expansion between bubbles would be so rapid that no light, no signal, no information could ever cross from one bubble to another. Each universe would be causally isolated, forever beyond the reach of the others. In this sense, there would be something beyond our universe. Not empty space, but other universes, other bubbles, in an endless, inflating cosmos. This is a type of multiverse, and it suggests that our universe is not everything that exists. It is just one pocket, one region, in a much larger structure. But notice how the question has shifted. We are no longer asking what our universe expands into. We are asking whether our universe is part of something larger, whether the word universe even refers to the totality of existence anymore. Another speculative framework comes from string theory, which attempts to unify quantum mechanics and gravity by proposing that the fundamental constituents of reality are tiny, vibrating strings rather than point-like particles. String theory requires extra dimensions beyond the three of space and one of time that we experience. And in some versions, it predicts an enormous number of possible universes, each with different properties, different physical constants, different laws. This collection of possibilities is sometimes called the landscape. Each point in the landscape represents a different kind of universe, a different way the fundamental laws could be arranged. And if eternal inflation is correct, each bubble universe might correspond to a different point in this landscape, exploring a different set of physical laws. In this view, there is not just something beyond our universe. There are countless somethings, countless other universes with their own physics, some so different from ours that matter could not exist, stars could not form, life could never arise. We happen to find ourselves in a universe with the right properties for existence because, well, we could not find ourselves anywhere else. There is also the concept of brain cosmology, which imagines our universe as a three-dimensional membrane, a brain embedded in a higher dimensional space called the bulk. Other brains could exist in this bulk, parallel to ours, separated by distances in the extra dimensions. These would be other universes, perhaps close to ours in the higher dimensional sense, yet completely unreachable because we cannot move through those extra dimensions. In some versions of brain cosmology, the Big Bang itself might have been the result of a collision between brains, a moment when two universes touched, and the energy of their collision gave birth to the hot, dense state from which our universe emerged. If this is true, then there is a sense in which our universe exists within something larger, even if that something is not a simple spatial container. Then there are cyclic models, which propose that the universe undergoes endless cycles of expansion and contraction. After expanding for trillions of years, the universe might eventually contract, collapsing back into a hot, dense state, only to bounce and expand again. Each cycle would be a new universe in a sense, though built from the remnants of the previous one. The beyond here is not spatial but temporal, an endless sequence of universes stretching into the past and future. There is also the many worlds interpretation of quantum mechanics, which suggests that every quantum event causes the universe to split into multiple branches, each representing a different outcome. This would create an unimaginably vast number of parallel universes, all branching from the same root, all equally real. But these parallel universes are not separated in space. They are separated in quantum configuration space, occupying the same locations but existing in different branches of the quantum wave function. All of these ideas, eternal inflation, the string landscape, brain cosmology, cyclic models, many worlds, they offer different versions of beyond. But notice what they have in common. None of them suggest that our universe is expanding into a simple, empty void. None of them give us the clean, intuitive answer we might have hoped for. Instead, they propose structures more complex, more abstract, more difficult to visualize than the question we started with. And we must remember, these are speculative. They are not confirmed by observation. Some of them may be forever beyond our ability to test, because they make predictions about regions of reality we can never access, events we can never observe, universes we can never reach. Science has always pushed the boundaries of the observable, using indirect evidence and mathematical consistency to infer what lies beyond direct perception. But there may be limits. There may be questions we can ask but never answer, structures we can imagine but never confirm, realities that exist but leave no trace we could ever detect. In the end, we return to where we began, standing beneath the stars, asking questions that may exceed our capacity to answer, yet unable to stop asking. So here we are at the end of our journey, and the question remains: if the universe is expanding, what is beyond it? We have traced the logic of expansion backward to the Big Bang. We have explored the geometry of space, the nature of infinity, the possibility of multiverses and higher dimensions. We have considered frameworks both established and speculative. And still, the answer slips through our fingers like water, refusing to solidify into something we can hold. This is unsettling. We are creatures who crave resolution. We want mysteries to be solved, questions to be answered, puzzles to click neatly into place. We want the universe to make sense, not just mathematically, but intuitively. We want it to conform to the patterns our minds were shaped to recognize. But the universe does not owe us this comfort. It operates according to principles that emerged long before minds existed to contemplate them. And some of those principles, when followed to their logical conclusions, lead us to places where intuition cannot follow. Perhaps this is as it should be. Consider how far we have come. A few thousand years ago, we thought the Earth was flat, the sky a dome, the stars mere lights embedded in crystal spheres. We could not imagine the true scale of the planet beneath our feet, much less the vastness of the cosmos beyond. Then we learned the Earth was round, spinning through space, orbiting a star that was itself just one among billions. We discovered galaxies, clusters, superclusters, structure upon structure extending farther than our ancestors could have dreamed. And now we know that even this vast observable universe might be just a tiny fraction of something far larger, perhaps infinitely larger, perhaps just one bubble among countless others. Each step outward has required us to abandon cherished assumptions. Each new discovery has made the cosmos stranger, less like the tidy, human-scaled world we thought we inhabited. And yet, with each step, our understanding has deepened. We have learned to ask better questions, to build better tools, to see farther and more clearly than the generation before. The question of what lies beyond the universe's expansion is perhaps the ultimate test of this process. It asks us to let go of the most fundamental assumption of all, the idea that everything must be inside something, that there must always be a next level, a larger container, a beyond. And the answer, such as it is, asks us to accept that beyond might not exist. Not as a place, not as a realm, not as anything we can point to or move toward or even conceptualize in spatial terms. The universe might be everything in a way that is complete and final. Not because there is a wall at the edge, but because the concept of an edge does not apply. This is what science offers us sometimes. Not satisfaction, but precision. Not comfort, but accuracy. The universe is under no obligation to be comprehensible, but it is under an obligation to be consistent. And our observations, our measurements, our theories, they all point toward a cosmos that is far stranger than we imagined, yet also far more ordered, far more lawful, than it might have been. We live in an age where we can measure the expansion of space itself, where we can observe light that has traveled for over 13 billion years, where we can map the structure of the cosmos on the largest scales. We can trace the history of the universe back to fractions of a second after its beginning. We can predict how it will evolve over trillions of years to come. This is extraordinary. This is a kind of understanding that no previous generation possessed. And yet, it comes with the recognition of limits. There are things we cannot know, regions of space we cannot observe, questions we cannot answer, not because we lack the intelligence or the tools, but because the nature of reality itself places them beyond our reach. The expansion continues. Galaxies recede, space stretches. The cosmic horizon grows farther away with each passing moment, carrying more and more of the universe beyond the boundary of what we can ever see, ever know, ever interact with. We are inhabitants of an expanding bubble of visibility, surrounded by a cosmos that extends far beyond our capacity to explore it. And perhaps that is fitting. Perhaps there is something beautiful in the recognition that we cannot know everything, that mystery is not a temporary condition, but a permanent feature of existence. We are finite beings in a possibly infinite universe, temporary sparks of consciousness in a cosmos that has existed for billions of years and will continue for billions more. We are made of atoms forged in the cores of ancient stars. We are structures of matter and energy, organized in such a way that we can contemplate our own existence. We are the universe looking at itself, asking questions about its own nature, pushing against the boundaries of understanding with curiosity and wonder. That we can ask what lies beyond the universe is itself remarkable. That we cannot fully answer the question does not diminish us. It reminds us of our place, not at the center, not as the purpose or pinnacle, but as participants, observers, questioners, temporary arrangements of matter that have achieved the capacity for awe. The stars will continue to shine. Space will continue to expand. Galaxies will drift farther apart, carried by forces we can measure but perhaps never fully understand. And somewhere, on a small planet orbiting an ordinary star, beings will look up at the night sky and wonder. They will ask questions. They will seek answers. They will push the boundaries of knowledge as far as they can be pushed. And when they reach the limits, when they arrive at questions that cannot be answered, they will do what we do now. They will marvel. They will contemplate. They will sit with the mystery and find in it not frustration, but a strange kind of peace. The expansion continues. The questions remain. And somewhere in the space between wonder and understanding, we find our place. Temporary, finite, yet connected to everything that is, was, or ever will be.